In the following slides, we will describe the basic element of videos. So we will briefly introduce how a video is constructed, how do we describe the elements in videos, and how do we represent the characteristic of a video. So basically, video is a sequence of images. So a nature video stream is continuous in both spatial and temporal domain. So we can say that images are information in the spatial domain, and by adding the temporal domain, a sequence of images form a video. So in order to represent and process a video stream digitally, it's necessary to sample spatially as well as temporally. So there may be an event occurring in the real world, and not only to sampling and the quantization in the spatial domain, so that we can see we can digitize the visual information at one time instance. We also have to sample in the temporal domain, because we cannot continuously store everything happening in the real world. We just can sample. We just can sample some of them to store in the computer system. So here is an illustration of the video stream. So in a nature scene, we may use a camera to perceive the visual information, and we have to quantize and sample visual information. And then to efficiently store the video data, we have to do data compression. And in the hardware system, we usually use the RGB color model to represent color information. But to more efficiently do data compression, we have to transform the RGB color space to C1 and C2 space. That is usually YCbCr space or YUV space. Okay, and then we can do some processing, storage, compression, or transmission. And we can store video data in a disk, and then from the disk we read the data, and we have to transform the color space from C1, C2 to RGB, so that we can display color information on the monitor, because the monitor uses RGB color space. So here is the digitization process as well as the display process of a video stream. So how do we represent video data? Actually, RGB is not very efficient for representing real-world imagery, because the equal bandwidths are required to describe all the three color components. So if we use we use 8 bits per component, we need 24 bits per pixel. But human eyes is more sensitive to luminance. As we said before, RGB color channel are not totally independent. So when one value increases, usually another two values also increase. So they are correlated. And for human perception, we perceive or we interpret a color based on luminance and hue and the saturation. So it's better to separate the luminous information from hue and the saturation information. And also, human eyes is more sensitive to luminance. So for more important information that is luminous, we can allocate more bits to represent luminous, but use fewer bits to represent hue and the saturation. And many image coding standard and broadcast system use luminous and color difference signal. and therefore YUV and YIQ color model are used for analog TV standard, and YCbCr color model is used for uh, digital video system. So the commonly used color models in video here, we can say that they are mostly derived from older analog method for coding color for TV. Okay, so luminous is separate from the color information, and there are several famous color model. YIQ is the color space used by the NTSC color TV system, and such color TV system mainly employed in North and Central America and Japan, as well as Taiwan. In Europe, video tape use PAL, and SECAM coding, which are based on TV that use a matrix transformation called YUV. Okay, and digital video mostly use matrix transformation called YCbCr, and YCbCr is closely related to YUV. So we can see several variations of the color model used in storing color information in videos. And here is the TV encoding systems distributed all around the world. So we can see that the PAL stands for phase alternating line. It's a color encoding system used in broadcast TV system in large part of the world. So we can see like PAL is used in mainland China, India, maybe half part of Africa, and most of Europe. And the SECAM, usually in French, that's for sequential color with memory, is an analog color television system first used in France, and we can see that it is also used in Russia and a part of Africa. And NTSC is the analog TV system in used in United States, Canada, Japan, South Korea, Taiwan, and the Philippines, Mexico. Among the various color models for representing color information in videos, we put more focus on the YUV color model and the YCbCr color model because they are widely adopted in video compression applications and systems. And the YUV color model defines a color space in terms of luminous and two chrominous components. So basically, this is similar. The idea of YUV is similar to HSV and HSI and LAB actually. And as we said before, separating the luminous information from the chrominous information is more effective for data compression. And the YUV color model is using the PAL, NTSC, and the SECAM composite color video standards. And YUV signals are created from an original RGB source, and the weighted value of RGB are added together to produce a single Y signal. So also based on the information we have mentioned above, the luminous information is basically the weighted sum of RGB. So Y is the luminous information, and the UV are actually chrominous information. The U signal is then created by subtracting the Y from the blue signal and then scaling. V is created by subtracting the Y from the red and then scaling. So here is the formula to transform RGB color space to YUV color space. So we can see that Y is weighted sum of RGB, and U is subtracting Y from blue with scaling. V is subtracting Y from red and scaling. And these formulas can be can also be simplified or be transformed to these formulas. So on the right side is a sample showing the original image and the corresponding YUV. So here on the top of the mountain, we can see the snow cover. So it is white and the intensity value is high. So here we can see that the Y value is larger on the top of the mountain. And here is UV. Here is you can see the blue and green, red and green, but actually they don't exactly represent blue and green and red information. No, it's just a representation showing the value of U. So if the value is positive, we use blue to represent. If the value is negative, we use green to represent. Okay, so this is an example showing YUV values. Another commonly used color model is called YCbCr. And YCbCr is a family of color space used in video and digital photography system. Also, Y is luminous component. CbCr are blue and red chroma component. And here is the formula to transform RGB to YCbCr. So we can see very complicated linear transformation between RGB and YCbCr. And basically, this kinds of transformation is defined based on many experiments, maybe also based on the psychological and industry experience. So on the right side is also a sample. So the original image, Y value, and the CbCr. Again, you can see something like yellow and blue, green and red on these two color plane, but actually they don't represent blue, yellow, red, and green. No, so they just represent the CB and the CR value. In addition to color space, another characteristic of videos that is distinct from images is called the Chroma Subsampling. Okay, as we mentioned before, we human eyes are more sensitive to luminous, but insensitive to chrominess. So, in view of this characteristic, when we want to compress video data, we actually can put more information, more bits, more resource on representing the luminous, but put less or fewer bits on representing chroma information. So here are four examples. If for each pixel we represent its intensity as well as the chroma, we use such representation. And if we just represent intensity information, we use this representation. So here, if we represent all information for each pixel, we say that it's a 4 by 4 by 4 scheme. Okay, so every information, including luminous and chrominous, are stored. And to achieve data compression, actually we can just store one chroma information per 2 sample. Okay, so this is called a 4 by 2 by 2 chroma subsampling scheme. That means we don't necessarily store the chroma information for every pixel. We just store it for every 2 pixels. And when we try to decompress the color information, we just copy the chroma information to the first, just copy the chroma information of the first pixel to the second pixel and then reconstruct. And because we human eyes are more sensitive to luminous and insensitive to chrominess, such chrominous distortion may not be sensible. Okay, so this is why we can do chroma subsampling. And also, we can do more compression if we adopt the 4x1x1 subsampling scheme. That means we store only one chroma information per 4 pixels, and we copy this chroma information to 3 others to reconstruct the color information. Okay, and also there's a scheme called 4x2x0. That means not horizontally, but also vertically. We just store one chroma information per 2 samples. So these for these 4 pixels, we just store the chrominess information of the average between the first and the third pixel, and then in reconstruction we copy it to all these 4 pixels, and this scheme is called 4x2x0. And this is a very important characteristic. Okay, chroma subsampling is an important technique to do data compression for video, especially for video. So here is an example. So given image resolution 720 by 576 pixel, and if we represent each color component by 8 bits, and the bit rate for the 4x4x4 scheme would be 10 megabits per frame. But if we do chroma subsampling, the size would be 5 megabits per frame, so almost half of the original one. But more importantly, visually we human eyes usually cannot discriminate the difference between images based on these 2 encoding schemes. So here, because we only store such volume of luminous, and we only store such volume of chrominess, so we can largely reduce the data, the bits we need to store such information. Another important characteristic of video is the motion. Because of the temporal domain, because of the sequence of image, successive video frames may contain the same objects that would be still or moving, and the motion estimation examines the movement of objects in an image sequence to try to obtain vectors representing the estimate motion. So motion information is also very important in video data compression, because we can expect that in 2 successive video frames, these 2 frames would be very similar, and the only difference between them would be the appearance of the moving object. For example, if there is a moving object here at time t, and at a time t plus 1, this object may move to here. So the only difference between these 2 videos would be the portion of this object covered. So if we can we can accurately estimate how this object moves, we can just store the motion vector, and all the other background information can keep the same, so that we don't have to restore it again. So by accurately estimate the motion, we can largely reduce the resource we have to store the video data. So this is why we put many focus on motion estimation in video analysis. In addition to video data compression, motion information is also very important for us to understand the behavior or the events occurring in video. So here is an example. So for two successive video frames, there is an object here, and then here is another, this object may move from the top to down. And how do we estimate the motion? Basically, we separate the video frame into many blocks or patches, and for each patch, we try to find the patches that the patches in the previous frame that is most similar to this current patch. Okay, so if we can accurately find this information, we will know that okay, this patch is original here, and then at the next frame this patch moved to this position. So by that we can estimate the motion vector, and motion vector is usually represent as the direction and the magnitude of the movement. And also, based on such estimation, we usually encode video frames with 3 different types. So especially in MPEG video, so this is a standard video compression standard. We usually have 3 types of frame: I frame, P frame, and B frame. I frame is called intra frame. So for intra frame, we encode everything. We encode all the information of all pixels. So in intra frame, we encode it without any temporal prediction. For P frame, P frame is the so-called forward predicted frame. So it's kind of interframe, and it's interframe encoded using motion prediction from the previous I frame or previous P frame. So using the predicted motion information, we can largely reduce the resource we have to allocate to store this frame. So in P frame, we will consider the motion information forward predicted. And for B frame, it's called a bidirectional predicted frame. So it's a kind of interframe encoded using the interplay motion prediction between the previous I or P frame and the next I or P frame. So in B frame, we estimate motion from previous I or P frame, as well as the successive I frame or P frame. So here is a figure to illustrate the idea. So for I frame, we encode everything, and we will encode intra frame at a specific time interval, okay, to avoid error propagation. And between 2 I frame, there will be several P frame. So for P frame, it uses the motion estimation predict from previous I or previous P frame. So it's forward predicted frame. And for B frame, the motion information in B frame is estimated based on comparing between the previous I X and the next P, the previous I and then the next P. Okay, so the motion is estimated bidirectionally. And then this example is actually extracted from the MPEG-2 video compression standard. So similarly, we can use many kinds of features to describe videos, and in the future we will deeply introduce these video features. And basically, video features can also be categorized into several groups. The first one is the motion-based features, like we can describe the camera motion, object motion, motion activity magnitude, and moving object detection. And we can also detect video shot change and extract the so-called shot-based feature. So we can extract the average shot length, the shot change frequency, and also we can divide videos into several scenes, and we can extract scene-based features. So for motion-based feature, we can describe camera motion and object motion. So for camera motion, that means the motion happens because of the camera move. Okay, and there may be several types of camera motion, like zoom in, zoom out, like rotation, like booming, that is moving up and down, like pan, that means the whole camera don't move, but the viewing angle may be changed, and also tilt. Okay, that means that may be change from left to right, that's called pan, and if it change from down to top to down, that is called tilt. And a dolly means the whole camera, the position of the camera move toward the subject or far from the subject. Okay, so we have several types of camera motion, and estimating camera motion is also very important in many applications. Okay, another motion may be issued by object, like the camera may be fixed, but because of the player running, so they will cause object motion. And then by checking the pattern of object motion, we can do a lot of applications. We can also measure the intensity or the magnitude of the motion. Like we can measure the intensity of activity, direction of activity, and as well as the spatial distribution and the temporal distribution of activity. So the spatial distribution means we can jointly consider the intensity as well as the orientation, the direction of this motion. So for example, we can divide the direction into 8 or 9 direction. Okay, for example, in this example, the moving direction is divided into 8 range, and we can count the numbers of pixels moving toward each range, and the intensity and their corresponding intensity, so that we can construct a motion histogram. We can also describe the temporal distribution, like the variation of activity over the duration of a video segment or shot. So maybe at the beginning, the motion activity is quite large, and maybe in the end of the video segment, the motion gradually decrease. And if we can detect a video shot change, we can extract several other video features, like the average shot length and the shot change frequency. And it's a statistical measurement which divides the total length of the film by the numbers of shots. So that's called the average duration of a shot between cuts. Okay, and the directors often change shot frequently to attract the audience. So when you watch TV, when you watch the commercial, you will perceive that higher shot change frequency occur in commercial segment, but not in TV show, because for the commercial segment, the director try to attract you, so they change the video shot very frequently to attract your attention. And the video segments with longer average shot length usually present peaceful scenes, like some director likes to take a very long shot to show the peaceful scenes, to show the very quiet event, to show the very quiet scene. Okay, so based on the average shot length and the shot change frequency, we can we can determine the characteristic of the corresponding video segment.